Okay, here I've got a system more or less balanced with magnets. We can calculate the moment of inertia if we know the masses of the magnets. At least we get an approximate moment of inertia if we know the masses of the magnets and their positions, and then also the information we need for this strap. Okay, so we'd probably be given the moment of inertia of the strap or formula. At this point, we won't do the integration until second semester. Okay, anyhow, so this is sort of in balance, and I'm going to hit the thing. I'm going to toss this magnet and hopefully hit that magnet and stick to it. Okay, so let's see what happens. Well, that was unusual. The magnet just bounced off. Well, that's kind of fortuitous because I kind of like that. I want to contrast that with what happens if the magnet sticks. It's the first time I've had it bounce off. Okay, so let's do it again. Well, let's get the thing where it was. It's bouncing off again. Well, that's pretty good. That's worth looking at. Okay, because you contrast that with what happens when the magnet sticks. Okay, so we're going to get that magnet to stick. Well, you don't want it to. Okay, it could be that I'm tossing the wrong side of the magnet. There, it's stuck. Okay, now, if you replay that, you'll see pretty clearly that when the magnet bounced off, the strap rotated further before it came to rest. And we want to know something about what's going on there. Okay, so assuming the magnet had the same speed all three times, and I think it was probably about the same, the magnet I tossed had a kinetic energy. Now, the system after the collision had a kinetic energy. Since the system moved further when the magnet bounced off than when it didn't, we can't say that the system afterwards had as much kinetic energy. The kinetic energy that the system gained from the collision, that the strap gained from the collision, the kinetic energy that the strap and the tossed magnet moving together had after the collision was less than the kinetic energy that the strap had when the magnet bounced off. Okay? So we don't think the kinetic energy was conserved in the collision, at least not in the second collision, or the last one where the magnets stuck together. So we want to kind of think of how we would analyze the kinetic energy of this sort of system. Well, when the strap rotated, and of course in lab we have a strap on much better bearings, couldn't hold that one up here and do the thing very easily, so I just used the shorter strap as a demonstration. But when we do this with the strap in the class, the strap is a little unbalanced, so if you don't give it too much energy, it's going to oscillate rather than make full revolutions. It's going to oscillate in simple harmonic motion. And what we want to understand is what the kinetic energy of that simple harmonic oscillation is, and then maybe what the kinetic energy of the projectile that strikes and sticks to the system might be. The other thing is that in both cases there's some dissipation of energy due to friction. Okay, in the case of the strap, friction's kind of high, the strap just kind of came to rest. It didn't try to oscillate, I don't think, I didn't watch, but it didn't oscillate, and it certainly didn't try to oscillate. Or it certainly didn't oscillate, and I don't think it even tried. With the better bearings, the system did oscillate. Well, let's look at what we have to analyze what's going on. Okay, first of all, we have kinetic energy. What's kinetic energy? Now, people still don't seem to understand where kinetic energy comes from or what it means. They might remember a formula, although that's shaky and it absolutely shouldn't be at this point of the course. So where does kinetic energy come from? Well, acceleration is equal to the rate of change of velocity and velocity is equal to the rate of change of position. So the primes, of course, indicate the derivative with respect to time. If you have a constant acceleration, then as everybody was able to do, like on the first day, you do some integration, and you can get a velocity function and a position function with some parameters to fill in. Each integration gives you an integration constant. Those constants will generally be considered to be the initial position, initial velocity. But you get this equation out of that. Okay? You should know how you get from constant acceleration through the integration to the equation, or from constant acceleration to a linear v versus t graph that'll tell you the same, that'll give you the same results. We take this, we plug in Newton's second law, which tells you the acceleration is F net over m, and we get definitions of work and kinetic energy, and I'm not going to go through that for 10th time. We need to know how that works, but it ultimately tells you then that the work done by the net force is the change in kinetic energy, and that it's also equal to F net delta x. Okay? So, well, that's a definition, okay, out of the substitution. We get the definition of kinetic energy as 1/2 mv squared, and the definition of work is the product of net force and displacement. Okay? So we get the work energy theorem. Work by the net force is equal to the change in kinetic energy. We have a parallel development that goes along almost exactly the same lines in most steps for rotational quantities. Okay, if you're in rotation, then you're talking about angular velocities measured in, for example, radians per second, that would be the standard unit, and angular accelerations and angular positions. The position is measured by angle. Angle is theta. Angular velocity is the rate of change of the angular position. So the derivative, the angular velocity is the derivative of angular position. Acceleration is the derivative of angular velocity. It's the rate of change of angular velocity. Angular acceleration, rate of change of angular velocity. Angular velocity is the rate of change of angular position. So the rate of change of angular velocity is the second derivative of the angular position. And these expressions are all equal to the angular acceleration, totally analogous to what you have here. So if you have a constant angular acceleration, you develop in exactly the same way, among other things, this equation. And then through another development where we define the moment of inertia as the sum of all the mr squareds, which is done very recently, get that kinetic energy is 1/2 I omega squared, where I is the sum again of all the mr squareds, or an integral, when we actually do integrals. Okay, other things we get, momentum is mv for motion along a line. And if you're moving in a plane or in space, you still get the same thing, where velocity and momentum are now vectors in the same direction, multiplier being mass. Angular velocity is I omega, or angular momentum is I omega, and that's actually a vector too. We haven't talked about the vector nature of it, because we want to get down to the basic idea first. So we'll talk about that a little later. And we have the analogy to net force equals mass times acceleration, which is net torque equals moment of inertia times acceleration. Okay? That's our scheme. And also, it follows in a way that you should understand that the work done by net force, by net torque, is product of the net torque and the angular displacement, analogous to net force times linear displacement. Okay. So if we want to analyze the kinetic energy of the rotating system, well, we've got to way of wherever it went, getting the kinetic energy if we can find the angular velocity. If we observe the angular position for a very short time after the collision, before it has time to change very much, we get a pretty good idea what the angular velocity is. Immediately after the collision, before friction slows it down. Or before restoring torque slows it down, which is the case with the beam. Well, since what we're looking at with the beam is a simple harmonic motion after the collision, we want to write down what we know about simple harmonic motion. Now we should be able to derive this. This comes directly from Newton's second law, which says mx double prime equals negative kx when you have a linear restoring force, the form negative kx. This immediately pops out. You can easily verify that this is a solution to this equation. For simple harmonic motion, you have a restoring torque. So you have torque times theta double prime equals negative k theta, which gives you the theta function here. Now, whether you want to derive that or not, you can do this by analogy with this, because this expression, this differential equation, this equation is totally analogous to this one with just different symbols. You end up with this solution. You should be able to do that, especially for this case. If you want to do this by imitation right now, it's okay. And then you know that the velocity is a derivative of the position, so you can easily take a derivative. And the acceleration is a derivative of velocity, which is a second derivative of position, so you can easily calculate that if you have this. Similarly here, you can get angular velocity of the rotating system or the angular acceleration by taking successive derivatives. Now, we have a little notational problem here, and I noticed that our primary textbook has the same notational problem. Using omega for the angular frequency of the simple harmonic motion, and omega for the angular velocity of the rotating system. Okay, that's not a good thing. So I kind of make a kind of an ugly omega here. Okay, I add a couple of curves to it. So I'm going to use that for the angular frequency involved with the reference circle. And we know the reference circle model. And then we're going to use the regular omega for angular velocity so we don't confuse the two. Okay? Now, for the beam with the magnets and the straps, we observed that after the object hit and was retained by the system, it moved out through a distance or an angular displacement of 3/10 of a radian before it returned and came back to the other side with a little less amplitude, so that when it came back it didn't go anywhere near 0.3 radians, it's more like half that, if that. Okay, that indicates that friction is dissipating energy. However, if we treat the system after collision as a first approximation, as if it was undergoing an angular simple harmonic motion with an amplitude of 0.3 radians, then we could analyze its energy. Now, moment of inertia is done as an approximation in my head because I don't have all the masses and everything. I think it's probably around 0.01 to 0.02 kilogram meter squared. So I'm going to say 0.016 kilogram meter squared. Amplitude is 0.3 radians. And we also observed that to get from here back to here and here took 18 seconds. Okay? That's enough information to do a pretty good analysis, to determine what the maximum kinetic energy in that simple harmonic motion is, so we kind of know the kinetic energy immediately after the collision, and to write the equation, do a good analysis. So, and we have to understand this, of course. Okay, if you go through one cycle in 18 seconds, a cycle doesn't correspond to 3/10 of a radian. People are going to want to divide the radians by the seconds, but you're not dividing the radians of the displacement by the number of seconds. Because if it only went up to 0.2 radians, it would still be oscillating at the same rate as we've clearly observed. Okay? So the amplitude of the oscillation doesn't determine its angular frequency. The quantity that goes there, the angular frequency, is determined by how many radians there are in a complete cycle and how long it takes to do a complete cycle. So that omega is the number of radians in a cycle divided by the time required for a cycle, and we get that to be about pi/9 radians per second. So that our equation, we have the amplitude, which is the 0.3 radians, that's the maximum angular displacement from equilibrium, and then we have the omega that goes in here, and I didn't put a phi in here, but there is that arbitrary constant, okay? And there would be a non-zero phi for this model if we start the clock at the instant of collision. So we'll put that in there. We're not going to worry about it. We just want to know about energy, okay? So what's the maximum kinetic energy during a cycle? Well, maximum kinetic energy during a cycle occurs when the thing is rotating most quickly, when its angular velocity is greatest. And the kinetic energy at any angular velocity we know is 1/2 I omega squared, so I'm going to say that the maximum kinetic energy during a cycle can be expressed as 1/2 I omega max squared. Okay? Now, what's omega max? What's the maximum kinetic energy in a cycle of simple harmonic motion? Well, it took a little while to see it, but right here is the equation for the angular velocity of the system at time t, and it's just the derivative of this, okay, or the derivative of this in general, and it's negative omega a sine of omega t, but it's the angular frequency omega, not the angular velocity omega. So we've got to be careful about that notation, and I'll kind of do the same thing down here so we know which omega we're talking about. So omega max occurs when this expression has its maximum value. Well, I asked people what the angular velocity looks like, you know, how this function behaves, and they kind of did this. Oh yeah, okay, it has this graph. Omega max occurs here. It didn't go far enough below the axis here, but you'd have negative omega max here. Okay. Well, that doesn't necessarily tell you what it is, but think about the sine. What's the maximum value a sine could have? Its maximum and minimum values, well, sine has values between -1 and 1. Okay? So the sine could take value -1, which would give you omega equals negative angular frequency omega times A. That would give you a positive angular frequency omega times A. So your omega max is just that angular frequency omega multiplied by A. Very easy to calculate if we understand how these things are all related. And especially if we understand where this comes from and where this comes from this equation and this equation. Again, you don't know how to solve those equations, but you ought to be able to prove that if I plug this into this equation, it works if omega equals the square root of k over m. And it does. In both cases, well, here omega would be square root of k over m. Here it turns out that this angular frequency omega is a square root of k over I. Now the k I have here has different units than the k I have here, because these quantities have different units than these. Still use k. And you see the analogy between these. I acts like mass in that it resists angular acceleration. Okay, the bigger your moment of inertia, the harder it is to provide a given acceleration to the system. Okay, so this analysis leads us to figuring out what the maximum kinetic, or what the kinetic energy of that system is just after it gets hit. At least it gives us an approximation. We haven't accounted for the energy loss to friction. So we're going to underestimate the maximum kinetic energy, but this is what we're going to get. And the maximum kinetic energy will, in fact, when you get the accurate maximum kinetic energy, that will, in fact, be the kinetic energy right after the collision. Since the system's losing energy to friction progressively after the collision. Now, if we want to correct for the work against friction, okay, well, here's your moment of inertia. I'm not sure what the angular acceleration is, although one of the first things we did in the first week was calculate the angular acceleration of a rotating beam. But let's just say it's negative 0.02 radians per second squared. Okay? So, in oscillating out to the extreme position, we lose energy to friction. And here we get what we need in order to calculate how much energy that is. Okay? How much work is done against friction through the 0.3 radians out to the maximum position? Well, first of all, the work done by friction, of course, work is equal to product of torque and angular displacement, the work of any force. And the work of a net force would be tau net times delta theta, but the work of the frictional force is this, okay? And under the influence of only friction, the net torque equals the frictional force, which will be I alpha where alpha is negative 0.02 radians per second squared. Well, we multiply this by I, we get the frictional torque, okay? Using the frictional torque, we multiply that by the 0.3 radians and we get the work done by friction, okay? Now, you're going to lose friction again coming back through another 0.3 radians, but that with the previous analysis can be combined to give us a good estimate of what the actual angular frequency was, or the actual kinetic energy of the rotating system was immediately after the collision. Now, the one big point is for the soon-to-be-taken midterm test, you should, at a minimum, know all this. If you've got to memorize it, okay. Much better if you can derive it. And we've been through that. And if you have to memorize these things, okay, they're really the same, except for the differences, minor differences in form. They come from very similar equations, and you really should know what this equation is. It just says net force here, that's mass times acceleration. And net force is negative kx. That's your premise for simple harmonic motion. And the analogous premise for angular simple harmonic motion. So you should be able to derive this. You should know things like the characteristics of the sine function. And it didn't seem that anybody remembered how to actually maximize a function using the techniques of first semester calculus. Take the derivative, set it equal to 0, critical points, etc. And you're just looking for where the derivative is 0, where the function is level, here, here, and here. But you don't need that. It was sufficient to know that the sine has values between negative 1 and 1 to be able to determine this. But you want this scheme. You want all of this and everything else that's related to it to be at your fingertips. Otherwise, you're not going to be able to think your way through problems. Be too busy trying to remember what's that formula. Okay? So, there it is. This is kind of an interesting analysis, and the questions in the test can go to the depth of this kind of analysis. Although, I don't realistically expect anybody to go into all this depth to be able to, but if you do, you'll impress me. You should at least be able to see what the relationships are and do some basic, get some basic results. Okay, so anyhow, there we have it.